Good afternoon, sir.
Yes, sir. Good afternoon, sir. Good afternoon.
Shall we start the session, sir?
Can you give me 2 minutes, sir? 2 minutes. Okay.
Okay, sir. Very good afternoon, participants. Welcome you all for a day 6 session 2 of AICTE sponsored 2 weeks online faculty development program on emerging trends and the challenges in a VLSI mixed signal processing for fourth industrial revolution. Welcome you all. Now I like to hand over the session to our resource person, Mr. Naveen Shankar, Field Application Engineer, Interpol Technologies. You can start, sir.
Participants will get started in another 2 minutes. Okay. Just give me some time. Okay.
Okay.
Good afternoon, participants. Sorry for the delay. I think it's right time to get started. Sir, can I share my screen, sir?
Yes, sir, you can share your screen, sir.
Yeah. Thank you, sir. Thank you. Participants, hope my screen is visible and my audio is clear. In case if there are any issues, please do let me know. Okay. So we stopped at the demonstration, right? So we stopped over here. So what all we had done was a quick recap on what we saw during the previous session. I think my screen share is paused. Yeah. Is my screen share visible? No?
Yes, sir, visible, sir.
Okay. Okay, fine. But I
You
can see
just
a
listen to
message.
our screens.
Like your screen sharing is paused.
Sir, and now your PPT screen is visible, sir.
Okay, okay. Just a second. I think I made a mistake.
But it is in a normal mode, sir, not in a slideshow mode, sir.
Yeah, yeah. Now is it visible, sir?
Yes, sir, visible, sir.
Yeah, yeah. Oh.
Yeah, okay, sir.
And the toolbar is also visible, right?
Yes, sir, visible, sir.
Yeah, yeah. Thank you, sir. Thank you.
Okay, sir.
So we stopped at I had demonstrated like how to create a schematic, okay, and for how to create a top level hierarchy for that. That is how to create a symbol and how to create a test circuit by using that symbol, and how to create a test circuit in order to make sure that the circuit behaves functionally correct. Okay. And then we went on with another circuit. Okay, so what we did is we created a .v file, that is an RTL design using Verilog as a HDL. Okay, created a imported that into Virtuoscope. Okay, by compiling the program, and then we created two views. One was a symbol and the other was functional. Okay, now what we have to do is we are going to combine the CMOS inverter and this .v file. Okay, inverter created out of a .v file. Okay, so let's see how to do that. Okay, so I'll create one more cell view. So I'll go to File, New, Cell View. Okay, and I'll name the design as buffer underscore test. Okay, buffer underscore test. Okay, I'll instantiate both the symbols. Okay, I'll go for add instance, and from the library that we had created earlier, one underscore buffer. Okay, first we instantiate the CMOS inverter. Okay, and then we instantiate the functional view inverter. Okay, it is not like you have to place the functional view inverter first and CMOS inverter next, not like that. Anyway, you'll be getting the output, but you have to understand the logic. Okay, suppose if we are connecting this inverter towards the output, okay, what will be the output signal, or how is the zeros and 1 going to be represented? Okay, please think about it. Meanwhile, we will see how to demonstrate. Okay, hope my question is clear. If we are interchanging the position of CMOS inverter and the inverter that we are created the using the Verilog program. Okay, if we swap the position, what will be the output? Okay, that is my question. Please think about it. And what will be the value of logic 0 and logic 1? That is my question. Okay, so we'll include an output port. Okay, so I'll name it as buff underscore out as the output port. Okay, I'll again go for add instance. Now we need the stimuli, right? So for that, I'll go for unlog lib. So the first one is supply voltage, which I'll mention as 3.3 volts. Okay, I'll have it over here. And then the pulse input. Okay, V pulse. Voltage 1 is 0 volt and voltage 2 is 3.3 volt. Period 20 nanoseconds. Delay time, I'll go for 10 nanoseconds. Rise time 1 pico. Fall time 1 pico. And pulse width 10 nanoseconds. Okay, so we click on hide and erase the source. And then I need the ground terminal, right? So I'll go for G and D. Click on hide and then place it once again. Okay, now use the wires and complete the connection. So I'll finish it off here. Okay, and then I have it like this. Okay, so I think you know how to do these connections because I've already demonstrated these things. Okay, now let us go for labeling. Okay, I have A, right, and then VDD, and then INV output of the first stage. Okay, let us see what happens. This is my A input stimuli, and then VDD. Okay, and then output of inverter. Okay, now I'll go for check and save, and like whatever we had done earlier using Spectre, we cannot run the simulation over here. A slight change. Okay, we have to create a config view. Okay, create a config view, assign the simulation engine. There it was Spectre. Okay, there the simulator was Spectre, but here the simulator is going to be AMS. Okay, we cannot use the AMS simulation engine directly because we need to specify what is going to be the target library and what is the um, target design flow. Okay, so for that is the reason why we cannot directly make use of the AMS design flow. So I'll close this and create a config view. So how to create a config view? I'll first select the cell, okay, for which the config view has to be created, and under view I'll choose a schematic. Okay, select the cell uh, which is for which config view has to be created, and under view select schematic. Now go to file, new, and select cell view. Okay, file, new, and cell view. Under type, choose the view as config. Under type, choose the view as config and click on OK. Right. The next one is go for use template. Okay, and here you'll have to choose the simulation engine. Okay, so to choose the simulation engine, go for this drop down, and this is the simulation engine that you have to select. Okay, AMS. Okay, select AMS and then select OK. Now again, in under top cell, okay, under top cell, the view has to be schematic. Under top cell, the view has to be schematic, and click on OK. Right. Now you have to update this view. Okay. How to update this? You can go for view and select update. Okay. Go for view and select update. Okay. The following cell views have been edited but not saved. Okay. So you have to save it. So just select OK. Right. And you can click on save the configuration, and you can also select you can also check. Okay, table view, tree view, you have two views, right? So both indicates like what are the libraries and what are the cells that you have created, what are the cells instantiated in the schematic. Okay, that particular cell view, you had already selected a cell view, right, under top cell. So in that cell view, what are the cells available, and what are the views available, etc. Okay, tree view also gives you the same details. Okay, you can also expand this, right? So now if you select open, it should bring back your buffer schematic test bench circuit that you had created for buffer design. Please remember that I had closed it earlier. Okay, you should not have this open and then create a configuration. You have to close it, and once you select open in hierarchical editor, it should get opened. Okay, now let us launch the ADEL window. So how to launch the ADEL window? I'll go for launch and select ADEL. Okay, here you'll have to go for setup. Under setup, choose simulator or directory or host. Okay, here the simulator has to be AMS again. Okay, the simulator is going to be AMS. Click on OK. Right. The next one that you have to do is the model library selection. The same thing here, it has to be nominal. Okay, click on apply and select OK. Right, and then the analysis. Okay, go for choose analysis and select transient. Okay, where you can mention the stop time as 100 nanoseconds, for example. Okay, nothing is fixed as of now. Okay, I'm just giving it in a random manner. Okay, so that we can get a clear reading. Okay, clear measurements, and it will be easier to view. Okay, so I'll go for moderate and select it. So we have got the type of analysis that is included over here. And the next one is selecting the input net and output net. Okay, that has for which the signals have to be displayed. I'll go for from design, select the input net of inverter, output net of the first stage inverter, and then output net of the overall circuit. Okay, output net of the overall circuit, and click on OK. Right, now you can run the simulation. So let us go back and run the simulation. If you go through the log file, you can see everything clear. Okay, let me show you the log file also. Okay, so simulation is still running. Participants, just give me some time. Let me check it out. Okay, so this is the error. Okay. Just a second, participants. Just give me some time. I'm just checking it out. This time repeating the steps because there was a net listing error. Okay, it was showing like some of the components were missing and there is no connection. Okay, so that is why I'm repeating the steps. Okay, just few minutes. Okay. Next I'm recreating the inverter once again. Okay, CMOS. Okay, think I didn't check the command interpreter window. Maybe if we had checked it, we would have got an idea. Okay, so I'll create a symbol for that. Okay, right. And then I'll create a circuit. Okay, since we have already checked the functionality of the inverter, I'm not creating the test bench circuit again. I'll just import the .b file, okay, that we had created. So go for import and select library. It's already there. Okay, cross check. That's one underscore locker, no issues. Okay, so I'll just import it. Okay, so here we have an error. Single inverter has a pin A that does not match HDL port list. Okay, cannot connect the terminal A in single inverter as it does not have a pin. Okay, so here we have the issue. Let us create it once again. Sorry. Okay, so now I'll go for okay. So now let us change the net name over here. I'll just open it with Gmail. Rename it as B. Okay. Okay. Even though we have ourselves for compilation messages. Okay. So let us create it or change this one. Just rename it as
Sir, excuse me, sir.
yes sir, yes. Hello.
Sir, your voice is somewhat low, sir.
Is it fine now?
Yeah, sir. Now fine, sir.
Okay sir, okay. Yeah,
Okay.
thank you. So edit, because we have made some changes to the pins, I'll just update it from the view. Okay, so can go for, you just open the symbol. Okay, go for edit and go for update pins from view. Okay, so you can just rename it. Okay, select OK and it gets included over here. Okay, you can just place it and remove this unwanted thing. Okay, I'll just select this and keep it over here. Okay, that's it. So you can again go for check and save, go back to your command interpreter window and check this, so we don't have any errors. Okay, so I'll close this once again. I'll check and save this once again, so I don't have any errors all over. Okay, so everything is fine now. Okay, so let me go back to command interpreter window and I'll import the Verilog file. Okay, inv.v, click on open and say okay. So I think there is an issue with this .p file. I've removed that. So let me recreate it. Okay, gedit invert.v. Okay, so I create module imd y. Okay, input a and output y. Okay, assign y is equal to negation of a and module. Okay, so I've completed this. We again go back to virtual soul and I'll import the Verilog file. So I'll select invert.v and the library as one underscore buffer. So there is some Sorry, participants. Just a second. Please give me some more time. Okay, just another 2 minutes. Okay. Everything, participants, right from the scratch. Okay, because there was an issue. Okay, since all the log file was available. Okay, previous data was also saved. Okay, we are unable to remove it completely. Okay, and that keeps on hitching at the back. Okay, so that is the reason I've completely removed everything and I'm doing it right from the scratch. Okay. Sorry, this is for and wire. Okay, so you can see we don't have any errors. So next I'll create the symbol. Okay, so yes, I have the VDD, I have the ground. Okay, let us go with this default symbol itself. I don't want to waste more time.
Hello, sir.
Hello. Yes, sir. Hello. Am I audible?
Not only audible, sir.
Yeah. Okay, sir. Okay. See, since I have some issues, I'm just recreating everything right from the scratch. Okay. So we have created the symbol. Okay. Next is the .v file. Let us create that. Okay. So think you should be aware of these things, right? Okay, so I'll just type in word.v. Okay, we are creating a new module. Okay, new module, and we'll type it inverter a comma y. Okay, now input. Okay, it is input pin. We are assigning it as A, and output pin we are assigning it as y. Okay, the expression or the operator. Okay, y is equal to negation of A, right? And then we end the module, right? So I'll save this, and we'll close this. Okay, and I don't want this terminal also. I'll just import the .p file to this virtual soap. Okay, so for verilog invert.v, and then one underscore buffer. Okay, so click on OK. Think, yeah, now it's fine. Okay, so verilog compiler was used for compilation, and we have created the symbol. Along with that, we have also created the functional view using virtual soap, right? So I'll close the log file. The next thing is I need the so you can see both the things over here. Now I need the buffer circuit. So I'll create a new cell view and name it as buff underscore test. Select OK. Get both the symbol. Okay. So I'll get this one. So this symbol over here. Click on hide and get it over here. Next is the inverter design. Okay, so let me have it over here, and then the output port. So first I'll get the output port, which I'll name it as buff underscore out. Okay, yes. So next again I'll go for add instance, analog lib VDC. Okay, DC voltage is 3.3 volt for VDD, and then this is for stimulant. Okay, repulse. Okay, voltage 1 is 0 volt and voltage 2 is 3.3. Period 20 nanoseconds, delay time 10 nanoseconds, rise time 1 pico, fall time 1 pico, and pulse width is 10 nanoseconds. Okay, click on hide and place it over here. Now we need the ground terminals. Okay, so I'll go for ground, click on hide and paste everything. Okay, now we'll go for the ground, wiring, connecting all the other terminals. Okay, and then we need the net names, right? So for that, let me go for the labels. Okay, we will finish it off these things and then complete the buffer. Okay, now let us go for the labels. VDD, okay, input net, and the output of first stage, which is 90 out. Okay, so this is the supply voltage. Okay, A, and your output of first stage. Go for check and save. In the command interpreter window, we don't have any errors, so the thing is fine. Now I'll do this, close this, and create a configuration view. Okay, so for that I'll select the schematic, go to file, new cell view. Okay, and then the type is config, right? and go for use template, select the simulation engine, which is AMS, and then top cell view has to be schematic. You go for update and save this, click on open. All right, so we have got it. Let us now go for the simulation part. So set up the simulator as AMS. Okay, and then again go for the model libraries. Okay, neutral or typical, whatever it is. Now the transient analysis for 100 nanoseconds, moderate, apply, okay, and the input and output signals that have to be blocked. Okay, done. Now let us run the simulation. Okay, so simulation is still going on. Okay, so it's getting okay. So again we are facing some issues with elaboration. Just a second. Maybe the issue with the CSHRC file. So let me close the other things. Just a second, participants. It's okay. So from the config view, let us launch the state. We have already saved the AMS state, right? So I'm just reloading it, and I'll run the simulation. Okay. Just a second, participants, please. Sorry for the delay.
Sir, Naveen sir?
Hello, yes sir, yes sir. Hello. Hello.
Sir, voice is not audible, sir.
Yes sir, because I was facing some issues, just I'm redoing everything right
Okay,
from
sir.
the scratch.
Okay, okay, sir.
Whatever we did in the previous session. That's it.
Oh, okay, sir.
That's
Now
why.
clear. Okay, okay, now clear, sir. Sir.
Hello.
Yes, sir.
Yes, just a second. Just finishing it off. Okay, so the circuit is now ready. Uh, Now let us check for the simulation results. Hope I am clear now. Okay. Yes. So let us create the configuration view. Okay. So I'll go for file, new cell view, and go for the type as config. Okay. And here under use template, I'll choose the simulator. Okay. And the top cell view also has to be schematic. Let's save it and we'll open the schematic. Okay. I'll launch the ADEL window again, and we'll go for setup, simulation or directory or host. Let us go for AMS. Okay, done. Now let us go for the analysis part. I'll run a transient analysis for 100 nanoseconds. Moderate, apply, OK. And then from the design, I'll select the input net, output of first stage and output of the second stage. Okay. Let us now run the simulation. Okay. So hope it should be fine now. Earlier we were getting some net listing errors. Okay. So yes, now it's fine. Okay. We were getting some net listing errors. That is the reason why we were not getting the output previously. Okay. And here you can see we have been talking about incisive, right? The compilation tool for HDL. Okay. So this is the tool for that. Okay. Just for running the simulation alone. Okay. And for compilation, NC-VLog. Okay. This is the name of Verilog compiler that is used in semi-custom IC design flow. Okay. The design is then elaborated and then mapped with the cadence virtuoso. Okay. You can see the elaborator tool option, and then it is coming into virtuoso spectral circuit simulator, and in that we are making use of AMS. Okay. And then we are going through the file. Okay. Library files, that is SCS file we have chosen, right? So with that SCS file we get these outputs. Okay. And I had asked you a question just before we started the simulation. Okay. So let us change the signal properties. Okay. I'll change the width also. So in the graph, I'll go for split all strips. So you can see this is your input, output of the first stage. Okay, output. So first stage in the sense, this is the first stage. So output of this stage is the functionality of an inverter, right? So it is correct. So when input is 0, output is 1. When input is 1, output is 0. So this fine, this one is fine. And then we have the output of buffer. Okay, this should be the same as your input, right? So this is what we were expecting, right? So any idea of the question that I had asked for? In case if you swap the position of these two, what would be the output? And what would be the value of logic 0 and logic 1? That was my question. Any answers for that? It has been nearly half an hour to 45 minutes since I asked the question. Any answers from the participants? I even have the chat open. Any answers? Any guess? Any guesses for that? Anybody? You can also unmute yourselves and let me know the answer. Anybody from the participants? Anybody participants, any answers? Okay, so let me explain that. Okay, so if you swap the position, what happens is the output of this inverter, okay, this is a CMOS inverter, right? So here you won't have any issues. Let me go back to the slide. Okay, just a second. Okay, let me go back to the slide. I'm just making use of pointer option. Let me create a new slide. Okay, so I have a new slide and I make use of the pointer. Okay, so the first one is your CMOS inverter, right? So I'll have a PMOS and NMOS transistor like this. So it'll be starting like this. Okay, and then here I have the NMOS transistor. So this goes to VDD, this goes to ground, and we take the output from here, and this goes to the digital block. Okay, so here we give the analog voltage as input, which is 3.3 volt. Okay, so the output also will be 3.3 at logic 1. Okay, if the input is 0, then output will be logic 1, that is 3.3 volt. So this is for CMOS inverter. But what about the digital block? If this is 3.3 volt, it will be equivalent. Its equivalent value is logic 1. Okay, so at this stage, your this value logic 0 will be 0, and the logic 1 value will be 3.3 volt. Okay, whereas at this stage it will be just zeros and ones. Okay, this will be just 0 and this will be just 1. This value will be 1. Okay, so that is the reason. Okay, since this is a digital block alone, this doesn't have any analog component, so it doesn't understand the voltage. Okay, just it will take the equivalent value. But how is it taking the equivalent value? Just we'll check as we move forward. Okay, so hope this is clear. In case if you have any doubts, you can let me know. Okay. So what we'll do next is we'll move into the example that we were planning to discuss. Okay, SAR ADC. So what is SAR ADC? Okay, so this is a data converter. Okay, which converts the analog waveform into discrete digital representation. So whatever we see, whatever we hear, everything, all the signals are analog in nature. So how to process this? How to convert the analog signal into digital signal? So I'm able to see some chat messages. Okay, just a second. Unable to see the slides. Okay. Is the slide visible now, participants? Hope the slide is visible now. I heard like from Pongodi ma'am was telling like we cannot see the slides. Hope the slides are visible now. Are the slides visible now? Yeah, thank you. Thanks for the response, Vinod sir. Yeah. So in order to convert the analog signals into digital form, okay, what we need to do is we need to sample the signal. Okay, first step will be sampling the signal, and then compare the value of voltages. When you are trying to compare the value of voltages, it is going to be an analog signal, right? So it has some value of voltage at a particular instance of time. Okay, so how to get that into digital form? So for that, we need a comparator. So output of that comparator, what will be the output of that comparator? It will be some value. Okay, and it has to be an equivalent to digital. Okay, how is it going to be an equivalent digital form? That is what we are going to understand using a SAR. Okay, successive approximation register. So let us see what is it based on. Okay, so this successive approximation register is based on a binary search algorithm. Okay, let me give you a real-time example. You can see a vegetable vendor who comes on the street, right? So he'll have a weighing balance. On one side, he'll include the fruits or vegetables, and on the other side, he'll keep including the weights in order to identify what is the unknown weight or what is the weight of the fruits or vegetables that you have selected. Okay, so that is the principle that you are going to make use of here. Okay, and uh, uh, this was invented in order to solve simple mathematical puzzle, which dates back to 1500s. Okay, that's what we are able to we are given in the slide. Okay, and this is the example. So here we have an unknown weight Ex. Okay, we have an unknown weight Ex. Okay, and in order to identify the value of this unknown weight, we'll keep on including known weights over here. Okay, so what are the known weights available for us? It is 1, 2, 4, 8, 16, and 32 kgs. Okay, so we'll first include a 32 kg weight over here. Okay, so what happens anyway? This unknown weight is larger, right? So it will be it will get inclined over here. Sorry, declined over here. Okay, so since it is declined, the output goes to the comparator. So what will be the comparator result? 32 is less than 45. Okay, or 32 is less than X. Okay, so if it is less than X, then that particular weight is retained. Okay, because along with this you should add some more weights, right? So this is retained. When a weight is retained, the output will be a logic 1. Okay, so the next one you are including the next highest weight possible, which is 16 kg. Okay, so if you add 16 kg along with the 32, what happens? So together it is 48 kg. So 48 kg is greater than 45. 48 kg is greater than 45, so it gets declined on this side. Okay, this is higher in mass, but this is lesser in mass. So what happens? You need not have this higher weight of 16 kg. So I'll remove that. If a weight is removed, then the equivalent digital value is going to be 0. Okay, likewise, I'll include the next highest possible weight. Okay, next largest possible weight, which is 8 kg. So 32 plus 8 is 40, right? 40 in the sense it is again less than X. So it is going to be retained, and the digital equivalent is going to be 1. Next, after 32 and 8, you are including one more 4 kg. So 32 plus 8 is 40, 40 plus 4 is 44. Okay, so 44 in the sense, even this is 44 is again less than X, right? So this also is going to be retained. So the logical equivalent is, digital equivalent is 1. And the next highest possible weight is 2 kg. Okay, so now 32 plus 8 plus 4 plus 2 is 46 kg, right? So 46 is greater than X. So it gets declined on this side. Okay, so if it is getting declined on this side, then it is going to be rejected. The 2 kg weight is going to be rejected. Okay, so the digital equivalent is 0. So likewise, it keeps on comparing the weights, and finally we get a digital equivalent. This is how your analog data is going to going to be converted into digital form. Okay, and this is the functional block diagram for a successive approximation register based analog to digital converter. Okay, so how does the blocks respond, and how is each and every block designed is what you are going to check next. Okay, so we have a timing block. We are not including that here, okay, in our illustration. So other than the timing block, we have all the other things. Okay, so analog input, okay, we give any type of signal. For example, let's assume a sinusoidal input signal, and it is sent into a sample and hold circuit. So why a sample and hold circuit? Okay, to acquire the input voltage. Okay, you acquire the input voltage, and it is a functionality of time, right? For each and every timing instance, you have a particular value of voltage. But how does the tool understand, how does the block understand? So that is the reason why we have a sampler. So what does the sampler do? It includes impulse response at each and every timing instance. If it is a positive, if the voltage is higher, then it has a positive impulse. If the voltage is low, okay, lower than the threshold, then it has a zero value, or the impulse value of impulse is 0. Okay, likewise, it keeps on including the signals, and then it gets multiplied by the respective value of voltages. Okay, respective value of voltages. Okay, and that value of voltage is going to be reformed. Okay, you are going to reconstruct the signal using that particular value of voltage. So there are chances of missing certain values. Okay, and that is what we call as quantization error. Okay, that is what we call as quantization error. Okay, we have a number of options in order to remove that quantization error. Okay, but here that is not going to be the that is going not the block which we are concentrating. Okay, so next to sample and hold circuit, you have a comparator which is used to compare the input voltage with the output of the digital to analog converter. Okay, and what is going to be the output of comparator circuit? It's going to send a data to the SAR register, successive approximation register. This successive approximation register is going to supply an approximate digital code of input voltage to the internal digital to analog converter. Okay, so the successive approximation register converts the analog data into digital form. Okay, and sends the output, the digital value, to the DAC, digital to analog converter. Okay, that digital to analog converter again reworks on the value of, on the digital data and converts it into a value of voltage. Okay, how was that converted into a value of voltage? You anyway, since it is a digital to analog converter, you have a reference voltage as input or supply voltage as an input. So with respect to that, it converts the digital data into analog. Okay, right? So this is what is happening in the successive approximation register. Okay, now uh, but how does this successive approximation register work? Initially, the most significant bit of the successive approximation register is initialized to a digital one. Okay, and then you are supplying that. Okay, so the MSB in the sense, for example, if it's a 4-bit data, then most significant bit is the leftmost bit, right? So the leftmost bit is set to 1 and the remaining bits will be set to 0. Okay, this will be fed to digital to analog converter. Okay, so the DAC supplies the equivalent analog voltage for that particular data, digital data. Okay, to the comparator. The comparator compares that with the input voltage and gives you the result. If it is less than 1, then you'll get a logic 1. If it is greater than the input, then you'll get a logic 0. That is how it goes on. Okay. And initially we had illustrated this design on ARCAD PSpice. Okay, because what you have in ARCAD PSpice is you have ICs, okay, from different vendors, say from Texas Instruments, On Semiconductor, analog devices. You have a number of devices. For example, if you are planning to design an amplifier, operational amplifier, you can just check for the available operational amplifiers in PSpice. Okay, give some input to that. Check all the performance parameters. Okay, like when you are designing an amplifier, gain is going to be the parameter for which you are going to work on. Okay, check the gain. So you get an idea of what you have to expect. Okay, what you have to expect. Then start designing it on cadence. Okay, you can use the you can uh, you can go for, sorry, uh, then start making use of it in the digital data. So you can build the operational amplifier using a MOSFET uh, or using FinFET or CNT-FET, latest technology nodes. Okay, and then you can check for its results so that you have a backgrounder of what to expect and what not to expect. Okay, So that is why we are going for ORCAD PSpice. And each and every block can be a separate experiment for students. Okay, so he can just design a comparator, okay, comparator circuit using a bipolar junction transistor, and you already have an ADC IC, ADC 0808, you will be having the IC, make use of that, okay, compare the output result. You, it is the student's duty to match the results. He should match the results of the ideal comparator with practical comparator. So that can be a very good lab experiment for them. Okay, so that is why we have designed on both ORCAD PSpice as well as on Cadence. First, we had designed it on ORCAD PSpice. Okay, the first block we created was a digital to analog converter. Okay, and for that we used a resistive ladder network. Okay, so what we did here was we used two resistor values, one with the base value R and the other one twice the value of base. Okay, for example, if the base values are, then the twice the value of base is 2R. Okay, so this ladder looks like this. Okay, so the ladder looks like this. Similar to resistive ladder network, you can also make use of capacitive ladder network. Both are fine, but for simplification and easier understanding, we have gone for a resistive ladder network. Okay, and then we are going to connect everything, all the resistors in parallel and series combination. If all the binary inputs are grounded, then the corresponding binary code is 0000. Okay, but how are we connecting everything? Okay, so we have to figure out the value of equivalent resistance. If all the inputs are connected to ground, then obviously the output is 000. But how to figure out the output voltage value? Okay, so you have to calculate the equivalent resistance at each and every stage. Okay, and finally you will get a circuit like this. Okay, and you can get the output voltage by using this formula. Okay, the same thing we have made use of in the uh, same operational amplifier. We are using it in ORCAD PSpice, and there in on Cadence we are designing it back practically. Okay, using CMOS transistors. Okay, and this is the principle. If any one of the input is connected to value of input voltage, okay, then the first one, if it is the first one, then the equivalent output voltage is going to be 1/16 of input, and if it is the second one, then it is going to be 1/8 of the input voltage. For third one, it is going to be 1/4 of the input voltage, and for the last one, it is going to be half the value of input voltage. So this is for a 4-bit DAC, but we have designed an 8-bit digital to analog converter. It can also be expanded, so this will be the equivalent value. Okay, if it is an 8-bit data, then you can figure out the value of output voltage using this formula. Okay, if it is going to be an n-bit data, okay, for example, if n is 16, then you can apply the value of 16 under n. Okay, instead of n, you can apply the value of 16 and calculate the output voltage. Okay, so this is a generalized expression. Okay, and now we have the circuit. Okay, this is an R2r Dac. We have made use of analog switches. Okay, and this is the resistive ladder network that we had built. Okay, and here you have the op amp. LM324 is the op amp that you have that is available from On Semiconductors, and we have made use of it. These are the input stimuli. Okay, 8 input stimuli. Since we have an 8-bit data. Okay, so it starts counting down from 256 down to 0. It starts counting. Okay, and then we have the successive approximation register. We have designed this using a D latch. Okay, D latch IC number, as you can see, it is 7474. Okay, it is a positive edge triggered D latch. Okay, and that is what we have here. We have a clock, we have a start conversion waveform, and according to that we have the clock generated for the input stage, okay, from the output stage of a previous one. Okay, and then we have a sample and hold circuit. So for sampling and hold, we have the IC number LF398, and for comparator, we have made use of an operational amplifier and length 324 itself. Okay, and what we have done here is, instead of making use of sample and hold circuit, what we can do is we can also make use of three values. Okay, for example, if your supply voltage is 3.3 volt, okay, you can figure out, you can check the response for three different values. One will be zero scale in the sense 0 volt, and the next one will be mid scale. So mid scale in the sense half the value of supply voltage. If the supply voltage is 3.3 volt, then half of that is 1.65, right? So that is called mid scale value. And the next one can be the value of VDD, okay, 3.3. That is going to be called as a full scale value. Okay. So using that, also you can figure out the analysis. You can check how it is getting counted. So what is going to be the start value? 8-bit in the sense it is it will, the highest value will be FF, okay, and the lowest value will be 0, 0. Okay, so that is how we have designed, and then we have created all the blocks individually. Okay, this is the DAC, this is the successive approximation register. Nothing but we have created a top level view. We have created a symbol for this successive approximation register, and we have made it, we have used it over here. This is the comparator, and here we have we are giving the values, okay, input voltages. Okay, and this is the stimuli. These are for the testing purpose. Even before you connect all the blocks, okay, it will be better to check individually. First, connect these two blocks and check for the output by giving some sort of stimuli. You know what to expect, right? So you give some sort of stimuli and check for the output. Then connect the comparator. Check the result of comparator at this stage and at this stage, and then finally check for the output. Okay, that is how we have done uh, circuits. Let me now demonstrate it on cadence. Okay, so we have seen this. Okay, so let me close this part. Okay, hope everything is fine till now. Okay, I have taken more time to debug the error that we were facing during the simulation, during the demonstration of AMS. So now let me go into the AMS design. So since it will take more time, what we have done is we have already captured the designs. Just I'm going to open that and run the simulation for you on cadence. Okay, so AMS, let me invoke the tool. Okay, let me invoke the tool first, and let me open the library. So first, we'll go into the SAR logic. Okay, so there we had made use of the D flop, right? So here here also, even here in cadence we have the standard cell library. Okay, if you go for JPDK 180 and search for DEFF. Okay, so you have the D flip flop over here. DFF is set and reset with the drive strength 1. Okay, making use of the circuit that are already available in the library itself. Okay, so this was a circuit for D flip flop. Okay, we have made use of this D flip flop over here in our successful approximation register. Okay, and these are the input stimuli that we have made use of. Okay, let me show you the simulation results. I'll just launch the ADEL state. We already have the state saved. Okay, just I'll reload it. Okay, and run the simulation. Fine. So it is for 100 microseconds. So it will take some time. Okay, we have the simulation results. So this is from the successive approximation register. Okay, so we can have a look at the digital data, right? So what I'll do is I'll split all the strips. Okay, you can see the waveforms. If the waveforms are not visible, you can please let me know. Anyway, I'll try to change the signal properties of all the waveforms. Is the other waveforms visible now? So I'll just change the properties. Solid, and I'll change the width to thick. Okay. So next I have the control bus and the digital data. Okay, and the digital data. So I'll go through this. Okay, so now to convert this analog data to digital. Okay, these are analog voltages, right? So how to convert it to digital? I'll go for measurements and I'll go for analog to digital. Okay, so here I'll have to select the signals which has to be connected converted to digital. So I selected 7 down to 0. It is an 8-bit data, right? So I'll choose 7 down to 0. Okay, center is going to be 0.5. Okay, and I need a bus, right? So it is going to be an unsigned decimal. Okay, unsigned decimal. Bus name is, I'll give it as Sar. Okay, if you click on OK, then I get the response over here. Okay, so the respective digital unsigned decimal data. So in the same way, if you want it to be hexadecimal, okay, even that you can do. You can go for measurements, go for analog to digital. Okay, I'll remove this. Select all the data. 7 down to 0. Okay, here what I'll do is I'll go for hexadecimal. Okay, Sar underscore hex. Okay, so if I scroll down, I can see, right? So this is the successive approximation register. And similarly, what I can do is I can show you the circuit for an R2r Dac. Okay, so R2r Dac, 8-bit R2r Dac, I have it over here. So I'll open the schematic. This is a practical R2r Dac. Okay, let me peep down this symbol. You have the ladder network, 8-bit ladder network. Okay, and here you have an operational amplifier. Okay, you have the operational amplifier. This is the circuit, right? So now let me, this is the practical R2R DAC. Okay, so now let me simulate this, right? I'll go for launch ADEL, load the state that is already there. Okay, DAC state. So I have the output over here. So let me take this these two outputs alone. One is the output of the DAC and the other one is the output of ladder network. Both has to be same. Okay, so I'll copy these two things to a new window and let us check whether it is counting or not. So for that, I'll go for analog to digital and I'll check the DAC pulsing. Okay, so let me have the center frequency as 0.5. and I'll make the bus. So this is for DAC, right? So I'll select OK. So you can see it starts counting. This is an unsigned decimal, right? So it is giving a decimal value. Okay. Similarly, if you wanted to have an analog, okay, so digital to analog data. So for this, if I want uh, binary or octal, okay, if I want a binary, then I can get that one also. And similarly, if you wanted hexadecimal value, okay, hexadecimal value or signed decimal value, so you can get those things also similarly. Okay, octal, okay, you can get those values, right? And similarly, what we have is even in the library in GPDK 180 standard cell, we have the uh, sorry, not in the library, we have it in AHDL lib. Okay, we have an ideal 8-bit ADC. Okay, ideal 8-bit ADC is available. So what we have done is we have created a test circuit so that we can compare the results, right? So what we have done is 8-bit DAC, okay, with both the ideal and practical circuits. Okay, so let me show that also. 8-bit test. This is what we have it. Okay, so both the results should match. The results of ideal circuits and the practical circuit should match. So let me launch the ADL window. Okay, launch the ADL window and run the simulation. Okay. Right, there will be some sort of variation because you have the NMOS transistors, right? MOSFET transistors. Because of that, you may get some variations. Okay, that is what you can see here. Okay, these two signals. Okay, this is the output of ideal circuit. This is the output of the ladder network, and this is the input to the comparator. Okay, and this is the ramp input signal that we are sending as the input. Okay, so this is the comparator circuit, comparison circuit, or testing the behavior. And then next we have the what we did is since we had completed R2r Dac and the Sar circuit, we just connected both of them together and we tested the output. Okay, this is how we did practical R2r Dac and the Sar logic. If you want, I can feed down to the circuit, okay, using the D flops, and this is going to be the R2r ladder network. Okay, 8-bit ladder network. So if we run the simulation, we can check out the results. Okay, you can compare the results actually, whatever is there. Okay. So now even in this stage, okay, what you can do is you can check for these analog to digital converted data. Okay, and similarly, what we had finally done is we had then included the comparator circuit. So what is the comparator that we had made use of? A 7-pack operational amplifier. Okay, so this is the comparator circuit. We have created a top level hierarchy. Okay, so if you peep down, it will be a 7-pack operational amplifier. Okay, with the current mirror load. Okay, so even this has been included, and finally we have a test bench circuit, which I'll open now. Okay, so this is the final successive approximation register circuit. Okay, so we have the R2r Dac, okay, your successive approximation register, and the comparator of a 7-pack operational amplifier. Okay, now if you try to check the simulation results, okay, so we can these are all the parameterized values. In case if you are really interested in figuring out how we got this, maybe in future, in the coming weeks, we are again starting with an online internship program. You can register for that and attend the programs. Okay, in case of how we arrived at these values. Okay, in case if you are interested in knowing how we arrived at these values. Okay. Uh, so now we are about to check out the simulation results for 8-bit successive approximation register, SAR based ADC. Okay, SAR based ADC. So let us check the results shortly. Okay, the simulation is still going on. Okay, so this is the result. And in case if you wanted to clarify what is going to be the digital data, then again I'll go for the measurements, analog to digital, and select all the digital equivalents. Okay, analog equivalents, so that I can get the digital data over here. So center is going to be 0.5, and I'll make a bus. I need the binary data, right? So SAR ADC out. I'll just name it as SAR ADC. I'll go for OK. So if you scroll down, you can see, you can also zoom in. Okay, zoom in and check what is the data. So this is for a decimal, right? Sorry, binary. In case if you wanted the hexadecimal values, and I'll again go for measurements, analog to digital. So I'll remove this. Okay, and select right from the beginning. QD7 down to 0. 4, 3, 2, 1, 0. And here we have it as, instead of binary, let me go for hexadecimal. And if you scroll down, you can figure out the value. Okay, so it will get reset after every cycle. Okay, reset in the sense it will again come back to 80 and then get executed once again. So this will be for let us check, go through the circuit and check what value it is. Okay, so this is for some intermediate value. So here I have given the input as 2 volt. Let us try. So this is the uh, input. Okay, analog input data. Okay, that is why we have named it as V in P. I'm just changing this value of voltage to 0. Okay, so 0 scale. I'm just checking the output at 0 scale. I'll check and save. There are 8 warnings because of these unconnected sources. Okay, these we had included these sources for testing purpose. Okay, so I'm just saving, and I'll rerun the simulation. Okay, so rerun the simulation right from this beginning for 8-bit Sar Adc. Okay, we have the simulation running. Let us check. Just few seconds, it will get over. Okay, so it's going on, about to get completed. Yes, and here we have the results. Okay, so let me, we will not check for the final waveform also, just we'll check for the digital data. Go for measurements, analog to digital, select QD down to QD7 down to 0. Okay, 0.5 Sar ADC. Okay, so select OK. So this is for 0 scale. Okay, you can see the difference. And let us check the same. You can see 80, 40, 20, 10, 8. It is all based on these signals that we had received. Okay, based on these inputs. Okay, the respective hexadecimal value at this range. Okay, suppose if we are planning to check for a full scale value. So what is the full scale value? It is based on the value of supply voltage. So we have to figure out what is the value of supply voltage. It is 3 volt. Now if we go for 3 volt, VDC is given as 3 volt. Let us check what happens. Okay, I'll just go for check and save, and I'll rerun the simulation. Okay, so in case if you have any doubts, you can let me know. Meanwhile, let the simulation get completed. Any doubts, participants, in both the sessions that we had in the morning as well as now? And I apologize for the time I took in order to debug the results, debug the circuit. So sorry for that. Otherwise, we could have had some more time for discussion. So any other queries, participants, related to morning session and whatever we had discussed now? Any queries until the simulation gets complete?
Dear participants, is there any queries? Please feel free to ask the resource person. You may unmute yourself to ask questions about the morning and evening sessions.
Yes. So here we have the final results for the analysis of full scale value. Okay, 3 volt. And if I convert this analog data into digital by going into measurements, analog to digital, and select the data QD7 down to 0. Okay, so now you can see this is for the full scale data. Okay, it goes to the maximum, so it changes, okay, with respect to the value of voltage that is given. If you give some intermediate data, then accordingly we have the approximations happening. Okay, every time for all the values it will not give the same results. Okay, there will be some changes. Just like how you measure the unknown weight from the vendor. Okay, uh, so here we had a regular weight of 45 kg. So we had the equivalent weights also. Suppose if the weight is somewhere around 33 kg, so we have some sort of quantization error there, right? We don't get exactly the 33 kg. Okay, or somewhere like 37 kg, we don't get it. Okay, so like that. Since we had weights of 1, 2, 4, 8, 16, and 32, we were able to get it. Suppose if we are getting, if we are having 5 kg and 7 kg and 10 kg, and we are asked to check for the unknown weight. Okay, so we'll not be getting the exact weight, right? There will be some sort of quantization error. So that's it. Okay. So any queries, participants? In what all topics, the topics that we had discussed.
Hello, sir.
Yes.
Sir, any free student version is there, sir, for students' point of view?
Version of what tool, sir?
When you are going, this is a cadence you are using. Any
Correct.
other simulation tools for free version?
ARCAD PSpice you have, sir. You have a evaluation version. ARCAD PSpice is available.
Okay, sir.
Yes, that will be useful.
Okay, sir. Thank you, sir.
Yeah. Any other queries, participants? And please do give me your feedback about both the sessions. Morning, I was able to see only 1 or 2 feedback, but I would like to see few other feedbacks also. One I already know. I lost some time in debugging, so that will be taken care of when we meet next time. Okay. Any other queries or any other feedback? Thank you, Vinod sir. Thanks for your feedback. Um, Anything else that you want to let me know or you wanted to discuss with me?
Hello, sir.
Yes.
Sir, can you teach the syllabus in Anna University, sir? What are the experiments they are having?
Yes, sir. We have some upcoming programs related to lab, right? VLSI lab, right?
Yes, sir.
We have an upcoming program. You can visit our website.
Okay, sir.
Even I can show you that. Okay, so you can visit our website for future programs. I think we are starting. Just a second. Even I'll get the result. I think we are starting one right from 30th March. Okay, that is going to be on analog. Anyway, I'll show that on the website also. Okay, so in ntuple.com, you can go to the trainings tab. Okay, and here you can check for VLSI programs. So you can see internship program, lab primer. So you are expecting lab experiments, right?
Yes, sir. Yes, sir. Yes, sir.
Here you can go for no more. Actually, we are starting with digital design, and here you can see the lab experiments, what all things are going to be discussed. Okay. Similarly, we'll be starting for analog also. I think that is from second week of March or something after this.
Okay, sir. Thank you, sir.
Tentatively, 31st March, sir. 31st March will be the start date.
Okay, sir.
For analog. Digital, I think you know the date here. Digital, it is 22nd Feb.
Okay, sir.
Okay, it has already started for digital. Yeah. Anything else, participants? Sir, may I know your name, please, sir? Hello.
Sir, I think Vinod Kumar, sir.
Okay, sir. Okay. He can also drop an email to me. Just I'll type my email ID on the chat. So it is naveen.shankar@ntupal.com, and I'll also give my contact number. Okay. In case if you have any queries, you can let me know. Or in case if you have any specific training inquiries, you can drop an email to my email ID, or you can just send me a WhatsApp message. Okay, so that I'll revert back, or one of my team members will revert back to you. Yeah. Anything else, participants, or any other queries? Any feedback?
Person. Okay, unmute yourself. You can directly ask our resource person. Otherwise, you put it chat.
Yeah, you can also let me know on the chat, or you can drop an email to my email ID. Anything is fine.
Sir, no more queries, sir.
Okay, sir. Okay.
Okay.
Yes.
So thank you, sir. Thank you very much, sir.
Yes, sir. So thank you all. Thanks for your patience. Let us get back together some other time in another program. Thank you all.
Thank you, sir. Thank you very much, sir.
Thank you.
So, dear participants, feedback link and attendance link are posted in chat box. The link available for 30 minutes. So, kindly fill the attendance link and feedback link.